Okay, hi everyone. So it's a great pleasure to have Mahesh Pandi speaking to us, giving this colloquium today. Mahesh is from the Okinawa Institute of Technology in Japan. So he is in the nonlinear and non-equilibrium physics unit there. So Mahesh has a huge, broad range of interests in a lot of things in statistical physics, non-equilibrium physics, and condensed matter. And right now, I think he's interested. His lists of interests include energy and sustainability, quantitative life sciences, statistical hydrodynamics, and amorphous media. Uh, Mahesh does really beautiful experiments on a variety of things in soft condensed matter and things like turbulence and so on. His academic trajectory has been like, I think he did a bachelor in computer science from University of Madras, and then he did two masters, one in electrical engineering and one in physics from University of Pittsburgh. And then he did a PhD again in University of Pittsburgh, working in, I think, non-equilibrium physics of turbulence. Uh, Again, he did some really beautiful experiments there. And after that, he was from 2006 to 2009. He was a postdoctoral fellow at Los Alamos National Laboratory. And from 2009 to 11, he was in Harvard. And since then, from 2012, he's been in Okinawa Institute. Uh, so today he's going to tell us about I think how N95 masks work and their physics. I suppose. So I first heard about this actually in a Twitter post by Nigel Goldenfeld, and I always wanted to know what these masks, how they work. So looking forward to this talk by Mahesh.
Thank you very much, Abhishek, and thank you everyone for having me over. I wish I was with you all in person because I love the ICTS campus, but because of all the complications we have to do with this online mode. Can you all hear me? I hope the audio is working fine. Uh,
Yeah.
so there is a reason why I am showing these Venetian masks from the carnival. It has a background to how this work started off. But before I do that, let me briefly introduce my work. Uh, okay. So as Abhishek introduced me, I work in experimental nonlinear, non-equilibrium and soft matter physics at OIST Japan, and my interests are in statistical hydrodynamics, mostly turbulence and interfacial flows. I also work in quantitative life sciences. My trajectory there has been a bit desultory. I spent many years just uh, uh, walking around the landscape, learning from learned colleagues who had uh, more focused research plans in quantitative life sciences. Uh, One of my areas that I started working by myself after arriving in Okinawa is statistical physics of energy and sustainability, especially fluctuations in wind energy and solar photovoltaics. And I have a long-standing interest in amorphous media. When I sat down to write this talk, I wondered which of these four areas does it fit into, and I think it falls closest in amorphous media because I'll be discussing disordered non-woven fabrics made of polymer fibers. So as I mentioned on the title slide, I showed you these Venetian masks because on February 22nd, I was actually passing through Venice. This is the scene outside the Santa Lucia station in Venice. I purchased my ticket to Trieste, where I was supposed to head to ICTP to teach at the Spring College on Physics of Complex Systems together with other wonderful colleagues. And this was the scene outside the train station. You see the Grand Canal up ahead, past the piazza, and it was all crowded. And it was crowded because the Venice Carnival was in progress, and you can see some of the people dressed up in fancy dresses and masks. Uh, And this was also just as the first COVID cases were breaking out in Lombardy and Veneto regions in Italy. And I have put a screenshot from BBC News on Feb 23rd, where they said the Venice Carnival was closed and Italy has imposed lockdown in some of the villages. So the school got cancelled. I video recorded the lectures to the extent I could, and then I returned back to Japan. Only this was the scene in Italy, and meanwhile in Japan there was a shortage of masks. And as many of you may know, the Japanese culture is such that at the first sign of a flu, all of us pull out face masks out of consideration for colleagues and neighbors. And people were beginning to get creative. In this photo from Japan Times, you can see this person wearing a Doraemon themed mask. And when I came back to Japan, couldn't find masks. And until this time, I did not know anything about N95 masks. I first read about them in media in about late February. I got curious and I started digging into the literature. There was nothing coherent. It was all scattered. But now there is a very good resource. Most of you may know about it. Our very own Shankar Ghosh and Arnab are part of n95decon.org. But it was either not up yet by then, but I only heard about it in early April. So the first question I had was, how does the N95 mask work? How does it manage to filter out more than 95% of particles of 0.3 microns or larger diameters? And once I started digging in and started understanding the basic ideas, the next one was, can I make one by myself? Because there were none to be found. Meanwhile, we were hearing reports from all over the world that there was a severe shortage of these N95 facepiece respirators due to breakdown of logistic supply chains. So the first resource I found was this study from 2006 by the National Academy of Sciences of the USA on reusability of face masks, where there's a chapter on the basic filtration mechanisms, and they detail that you have basically competing requirements that are that one faces in designing a filtration respirator. You need a small enough pore size to block out the particles, but if you have pore size too small, then respiration becomes very difficult. So you have to find an optimal pore diameter, and the filtration of small particles follows a different mechanism than filtration of large particles. So a range of strategies are adopted. And this document explains that basically there are three primary mechanisms. First is inertial impaction, the second is called diffusion, and third is called electrostatic attraction. When your particles have 1 micron or larger diameter, the understanding is that these particles can deviate from streamlines, the hydrodynamic streamlines, and then they slam into the filtration fabric and they get trapped there. But if the particles have 1 micron or less diameter, then they follow the streamlines, but they are susceptible to thermal fluctuations, and so they diffuse, and then they can get trapped by the filtration layers. This 1 micron threshold is basically, to my understanding, coming from colloidal physics. This document itself did not say anything about where this 1 micron threshold came from. But when we study colloidal physics, we say if you want a colloidal particle that is responding to thermal fluctuation, we say we should stick to about 1 micron or lower diameter. But that does not really explain why it should follow inertial impaction if it is greater than 1 micron. Since I do come from a background in experimental fluid dynamics, turbulence in particular, we use an experimental technique called particle imaging velocimetry or particle tracking velocimetry, where we seed the flow with tiny particles and we image their motion with fast cameras. And a lot of effort goes into the optical scattering properties of the particles, etc. But the one thing that we make sure is that the particles are small enough to follow the streamlines, because they are passive tracers, as we call them. And the parameter that determines whether the seeded particles are following this, are passive or inertial, is decided by what we call the Stokes number. I'm not explaining the Stokes number here, but when we do the Stokes number calculation, which is basically the ratio of the response time of the particle to response time of the flow in unbounded flow, or it could be near an obstacle. If it is of the order of 1, then we say it is non-inertial or passive tracer. And usually in the kind of flows we expect to observe in filtration layers, because they are porous media and they follow what we call Darcy's law of fluid flow. Darcy's law, for those of you who are students in the audience, is nothing but the Ohm's law of fluids. So when we think of Ohm's law, we say voltage goes as current times resistance. So current is a velocity and voltage is like a pressure gradient in the fluid flow. So it's like the force. So it's like the F equals ma, the Newton's second law of motion. Only Ohm's law is telling us that force is going proportional to velocity and not proportional to the acceleration or the rate of change of velocity. And in porous media also, flows in porous media face this Darcy's law, because the pressure gradient becomes proportional to the velocity. So there, when we apply the response times that one would expect from the flow rates there, the particle diameter at which I expect to see inertial effects would be of the order of 10 microns. So there is some discrepancy in the way this has been explained in the document, but I'm simply reviewing what was given in the document as I started digging in. So I explained the inertial impaction and the diffusion, but what we hear about being the most efficient mechanism of filtration is electrostatic attraction. In this, what happens is the filtration fabric that you have in the respirator or the mask has static charge. You could induce static charge through various mechanisms. We'll come to that in later slides. But basically, if your virus particles or bacteria or dust particles that you're trying to filter against are charged, then there is are oppositely charged to the charge of your filtration fabric, then the long-range Coulomb force will attract these particles, and they are trapped in the fabric layer. And once they are trapped, the van der Waals forces will hold them in place. So that is the basic argument. But to my knowledge, I don't claim to be an expert in filtration theory or filtration mechanisms, but as I started studying the literature, I realized most of this field is actually rooted in semi-empirical analysis. Robust theoretical results or theory or fundamental understanding is quite hard to come by here. So most of the results that are known today have come from basically trial and error through tinkering. Now, I've used Zoom, but this is the first time I'm presenting via Zoom, so I apologize in advance if I make mistakes as I move forward or backward in my slides. Okay, so as I mentioned, there are these three mechanisms, and the argument is that electrostatic attraction is by far the most efficient of these three. And this mechanism has been around for about 5 to 6 decades from the literature that I looked into. The last reference that I'm highlighting here with the spotlight by Frederick, Some Effects of Electrostatic Charges, is from 1974. That was the earliest review in literature I could find. And according to that that reference, the first fabrics were basically cotton or wool, natural fibers that were triboelectrically charged. That means they took two dissimilar fabrics and they rubbed them together to induce charges. And then over time, they started adding resins to them to improve the electrostatic charge retention. But it became a problem because these resins could not work against oil-based aerosol droplets, which can screen charges. So eventually, people worked out that class of polymeric fabrics called electric fabrics, which have embedded charges within them. That is, they're naturally statically charged. We know this from, for example, when we play with thermocol, as we call in India, or styrofoam, as it is called in the Western, in the Occident. Packaging material, it tends to stick to our fabric because these polystyrene polymers are naturally electrocharged. So I started looking into electrocharged fabrics and how they are made, etc. So most of the discussion today will be about how these things are made and how I ended up trying to make them, starting in my garage actually. So one of the methods by which it is made is a method called electrospinning. In this, you have a syringe pump in which you load either a molten polymer, which is more rare. Usually they dissolve polymer in an organic solvent, and it is pumped out. You apply pressure and you generate a drop, and you apply a high voltage electric field between the syringe pump, which I call the emitter, and a drum or a plate that is held some distance away, which I'll call the collector. And this the pressure head from the syringe pump is initiating the jet, and once it emerges, the high voltage electric field accelerates it and stretches this non-Newtonian fluid. So it is basically undergoing a case of extensional rheology. And I'm showing this video that I have borrowed from a group at Shinshu University in Matsumoto, Japan. It's beautiful to look at. The problem, so this method can use any type of polymer. Basically, it is agnostic to the polymer type, but the throughput is low because you have to, it scales linearly with the number of syringes you are using. Also, one of I'm giving away some of the details in advance. When I started to design my own fabrication setup, my intent was to do something with commonly available parts with simple methods. And organic solvents are not easily available for the layperson. So I decided against dissolved polymer solutions. I also decided against electrospinning because high voltage electric fields are difficult to set up for the layperson. The second method, which is actually the most common method used for manufacturing the electrocharged filtration layers for the N95 respirators, is known as melt blowing. Melt blowing is basically you have a polymer melt that is forced through a conical die with an orifice at the end, and you blow pressurized hot air from two sides to stretch the jet as it is coming out, and it forms a fiber. And as it is being accelerated by the hot air, there is a jet of cold air to cool it down so that it solidifies and lands on a conveyor belt. And here is a video that I took from a Chinese company, as a promotional video on YouTube, where they show how this is being made. This is also agnostic to the polymer type, and it is easily scalable, but it is inherently suited for large volume manufacturing because you have to deal with pressurized hot air and the die geometry. It's not easy to construct it with common parts. So then comes the method that I tried. I'm not aware of anyone who has tried this method before, which is what we know the world over as the cotton candy machine. I know for a fact that Manu Prakash at Stanford has also independently come up with the same method, and they have done some very nice work in their lab to make same electrocharged filtration fabrics. I was not aware of his work, and I don't think he was aware of my work until we both got well underway. Anyway, the basic idea is you have a cylindrical drum within which at the center you have what I'll call the emitter. As this gentleman in this video is doing, he has basically lit a heat source and he put it under this emitter, and he is going to pour some sugar, sugar mixed with water. Usually they mix 1 part of water and 3 parts of sugar, and which it gets heated and gets caramelized. So it becomes a non-Newtonian solution. And when he starts spinning the emitter, the centrifugal force is basically competing with the capillary force. There are tiny holes or orifices along the cylindrical wall of the emitter, as I've shown in this schematic with these tiny red dots. So these orifices, the solution starts coming out of the orifices, and the centrifugal force then splays apart the jet that is initiated, and it goes in a spiral trajectory as shown here. You can follow my spotlight, and it results in this candy floss or cotton candy as we know it. The basic idea, the basic physics behind this was worked out in this paper by Paula Meado and co-workers in 2011. And the reason I heard about it was because of this paper. In 2010, when I was a postdoc at Harvard, my postdoc advisor Mahadevan actually mentioned it in passing that you can use the cotton candy machine to make polymeric nanofibers. And he was working with Paula. I think this was the paper that resulted from that effort, where they basically showed that there are two stages to making these nanofibers, polymeric fibers. In the first stage, you are initiating the jet, where the capillary force is competing with the centrifugal force. And when you balance the two, I'm not giving you the calculation here. It is in the paper that I have referenced here below. When you balance them both, you get a threshold angular velocity at which the jet can be initiated. So the angular velocity goes as the threshold angular velocity goes as square root of sigma, which is the surface tension of your liquid, divided by R0 squared. RO. R subscript O is the orifice radius, the radius of the tiny holes on the emitter wall. Capital R sub E is the emitter radius, and rho is the density of your polymeric solution. In the second stage, once you have initiated the jet, it is now going to get forced out of the orifice, and it will execute the spiral trajectory. And that is a case of extensional rheology, as I said. There you have viscous force competing with the centrifugal force. And when you balance these two, they showed that you can actually show that the mean radius or the average radius of the fibers that are generated scale as this expression. This should have been, this is the orifice radius times the square root of velocity at the time the jet is ejected from the orifice. As it traverses in the spiral trajectory, it is of course going to slow down, but that is not the velocity they take. They take the velocity at the time that the jet is initiated. Nu is the kinematic viscosity. Kinematic viscosity is basically the viscosity of the dynamical viscosity of your fluid divided by the density. In here, since we are dealing with a non-Newtonian fluid, this is not your normal viscosity. It is what we call extensional viscosity, divided by the radius of your collector, so distance to the collector to the power 3/2, and the angular velocity. So most of these parameters that I have listed here, they enter through the design specification for the fabrication setup. The ones that are material dependent are the surface tension, the density, and the viscosity, basically, And these are controlled through the temperature. How high a temperature are you going to raise the polymeric solution to, or the non-Newtonian solution to? I will show later the materials that I played with, and I will discuss how these material parameters vary and what temperatures I picked. So this is the basic system. And as you saw in this video earlier, he was using a pretty simple setup. He had something like a kerosene lamp here. Oops, sorry. So he's got a kerosene lamp with 2 wicks that he's lighting up, and he puts it under this cylindrical emitter, and he goes to work by just spinning the emitter with a cycle wheel sort of geared mechanism. So now, how do we translate these parameters to the design? So now I've basically stopped the physics part of it, and it wasn't even physics that I worked out. It was worked out by Paula and Maha and Kit Parker and co-workers. Then I started around late February, early March. I started trying to build my own cotton candy machine in my garage. And so the materials I played with are polypropylene and polystyrene polymers. In polypropylene, I played with what is known as isotactic propylene, and the other one was low crystalline propylene. I initially called it amorphous propylene. I learned later that that is the wrong terminology. Apparently, amorphous polypropylene exists, and it is very hard to find. I call it low crystallinity polypropylene because I took basically caps of discarded PET bottles. If you can see my video, these caps. So basically, these are the low crystalline polypropylene. I was taking them and I was sort of doing a simple autoclaving decontamination procedure in a pressure cooker in my kitchen, and threw them into a blender like a Sumit Mixi type, and just turn it into powder and put it in the cotton candy machine. I used flame torch initially to heat up the polymer and melt it, and went to work. But by trial and error and by reading in literature, so the particular literature I want to cite this last, the third reference I have shown here from 2018. I don't even know how to pronounce Wongpajan, I don't know. But this paper is the one that from where I got most of the material specific details about the right temperature, viscosity, etc. So I was standing on the shoulders of all those giants in time while I was tinkering around with this. So I used high molecular weight polypropylene. That is what I figured by trial and error is the better one to use, because if you use low molecular weight, it is brittle. So if you make, it's not that you cannot make an electrocharged fabric, but if you make it, it breaks up easily. If you're using polystyrene, polystyrene has very high static charge retention property. But if you use polystyrene, you should use what is called general purpose polystyrene. That is the kind of material used for the CD covers, CD cases. You should not use expanded polystyrene, which is the one we use for packaging, like thermocol. That is not the one that will work. So I played with either isotactic polypropylene at high molecular weight, or I mixed this low crystalline polypropylene with polystyrene mixture. They are not miscible, so I just mixed the granules and melted them together and played with it. The temperature range at which I was, yeah.
I think Abhishek has a question. His hands is
Absolutely,
raised.
yes.
Yeah, maybe so Mahesh, you can hear me, right?
Yes, yes.
Yeah, so maybe you'll say, but I just wanted to get something clarified. So you want finally to make a mesh where the fiber size has to be of some particular size and it has to be charged. Is that like what you're looking for?
Yes, yes.
Okay, and the
I'm
size
sorry,
is like...
yeah, please go ahead.
Yeah, so the size you want is like in nanometers. That's the size of the radius of the fibers. And but then I mean finally there are lots of parameters, right? I mean, what exactly are you looking for when you do these trials and errors?
Okay, so basically I'm using these two relations, the threshold angular velocity and the mean radius. So let me give you the story slightly in reverse. What I first did was I managed to find one N95 mask and cut it open and took out its electrocharged filtration layer. And I put it under a scanning electron microscope, and I got the distribution of the fiber diameters that they had. But I did not know what material they were using. I managed to get hold of a potentiometer to measure the amount of static charge on this electrocharged layer from the N95. So I was trying to reverse engineer the material. So Using these two relations, I was trying to tweak the mean fiber diameter, and I was trying to get as close to the static charge properties of the layers that the commercial N95 masks were exhibiting. So that was the goal. I'm sorry that I did not come through clearly because I made this presentation in a bit of a hurry, so I'm not very satisfied with the way I have done it. Can I go ahead?
Yeah,
okay.
Thanks.
Yeah. So this is probably,
Mahesh,
please.
I think there is another question by Abhijit.
Yeah.
Abhijit, would you go on?
Hello.
Hello. Yes.
Yeah. So you're saying the diffusion mechanism holds for particles less than 1 micron size.
That is what is claimed in this National Academy's report, but they don't explain how that. They don't explain how they arrived at the number.
Okay, but our virus diameter is around 0.1 micrometer. So is it really necessary? I mean, is the electrostatic mechanism is really necessary to filter out or to block the virus?
You will see the results from the electrocharged fabric and the non-electrocharged fabric, and you will see that there is a difference. So that will be towards the end. So let me go through this is the boring part, because this was where 99% perspiration, as Edison would have said, went in trying to tweak and figure out the parameter ranges. So we used the polypropylene or the polypropylene polystyrene mixture, and the temperature range, which I figured from the previous reference, was in the range of 280 to 340 degrees Celsius. And for jet initiation, from simple calculation, I could see that the threshold angular velocity should be around 2,450 RPM, revolutions per minute. Sorry, should be around 4,500 RPM. But I was seeing fibers being generated at 2,450 RPM. So you should take those two expressions I showed in the earlier slide as ballpark estimates. They're order of magnitude estimates. Now, in trying to figure out how to make the emitter cylinder spin, I figured you could use an electric drill or a Dremel. These are some of the. So initially, I used basically a soda can or a beer can, and I put a drill through it and made it. And I drilled tiny holes of hundreds of microns radius along the wall, and basically, if you use an electric drill, you can easily get up to 3,000 or 4,000 RPM. I used what is known as a Dremel tool. You can control the RPM in different stages, and you can go up to 35,000 RPM. I was working in the range of 10 to 15,000 RPM. And so after, another thing I want to point out is, if you are working with a commercial cotton candy machine, they usually come with this mesh, which is of the order of millimeters, or they come with these vertical slats or diagonal slats. Then you tend to not get as good fiber diameter. So I replaced this mesh with basically the aluminum can with holes drilled to lower diameters that I wanted. And this was from one of the early videos. You can see this was a commercial cotton candy machine. The first one died, unfortunately, but by then we were able to get delivery of this, and I changed the emitter, and this is the fabric that we were generating for polypropylene. So it was very simple. Most of these commercial machines are either electrically heated or gas heated. So either one works. All you need is to basically melt the polymer to a high enough temperature, and then you're in business, and you get this. Once getting these fibers itself was very easy. There was nothing special at all in doing that. But then it was tweaking the orifice radius and other parameters to get fibers of the right diameter that took a lot of the tinkering effort. So the basic process was, once the tinkering was done and I was able to generate the fibers in this cotton candy machine, you get something like this, and fibers in this concentric geometry. I just sandwiched them in between two glass plates that were lying around in my lab, and generated this fabric. So you can, if you can look at my video, then you'll probably see I'm holding one of those fabrics. So what we basically sandwiched them and got these. These are about they are slightly more dense than the commercial N95 electrocharged layer. We don't have that kind of quality control, but it was working fine. So once we have the fabric, what about the electrocharging filtration characteristics, as the question was raised? So unfortunately, the amount of charge on it was not as high as we would have liked. So I'll explain what I mean by that shortly. When people talk about these electret polymers or electrocharged filtration fabrics, there are two kinds. One is called a space charge or a real charge electret, which has basically embedded charges in it. So the material itself has the polymer molecules themselves have dangling ions at their periphery, which give basically a static field, electric field to the material once you fabricate it. Or you can take a polymeric, non-woven polymer fabric, and you can apply an external field to orient the dipoles within the polymer material. And there are several ways to do it. One common way we know is triboelectric charging, where you take two dissimilar fabrics and rub them together until one of them acquires a positive charge and the other one acquires a negative charge. Another method is called thermal charging, where you take the polymer melt at the time that the polymer is being molten in this emitter and it is being thrown out. You apply an external field between the emitter and the collector, like I showed in the case of electro spinning few slides ago. So as you saw in this one, you apply a high voltage electric field between the collector and the emitter, and that will also that will induce or orient the dipoles in the polymer. So I tried that as one method, basically by taking a car battery and applying a voltage across, and that did induce some. Another method is called electron or ion beam charging. I did not have access to that method at all. And one is called photoelectret charging. Photoelectret charging works in usually polymeric, what are these called? Photovoltaic systems. The polypropylene and polystyrene are not that kind of materials, as I learned. The one method that was easiest to implement was isothermal charging. It is very easy to achieve using one commonly available part, which basically indoor air purifiers. The way they work is they have two electrodes with high voltage across these two electrodes, and as the air goes past them, basically there is dielectric breakdown of air, and it charges the particles, the dust particles or the bacterial or viral particles that are going past, and they get trapped by a charged plate. And the air that is coming out the other end, that is entering the room, is devoid of these dust particles and such. Now there are two types of these purifiers. Negative ion air purifiers are the ones that you should be using, not the balanced ion generators, which generate both positive and negative ions. I first tried it with that, and I realized to my dismay that whatever little electrocharging was present in it was lost, because I was getting an equal fraction of both positive and negative charges onto the fabric. So basically, this is the system I got off Amazon for $150. It's from a company called Mystic Marvels in US. It operates at 9 kilovolts, and here is a blown up image of the end where I basically hold the electrocharged the polymer fabric. So you have one electrode coming out and the other electrode is inside. So as the air is being blown, the negative ions are basically getting onto the electrocharged layer. That is the principle of isothermal charging. and we were holding it for about 10 minutes. We did trial and error for 1 minute, 2 minute, up to 10-minute durations, and measured the amount of static charge. And so first, let me show you the results we saw. In this table, I'm measuring the electrostatic potential in kilovolts using a potentiometer. For an N95 facepiece respirator, we got about 11.1 kilovolts. Now, when I'm saying these are the measurements I made, of course, it matters at what distance was I measuring it from the surface of the fabric. So the potentiometer that I purchased, it was available within Japan, so we could get it easily. It comes with a sensor that has a piezo transducer. So basically, you hold the sensor stick to the fabric, and the piezo transducer moves back and forth and measures the amount of voltage it is sensing at a distance of about 50 to 100 nanometers from the fabric. So the values I am quoting are coming from such a measurement. So for the N95 facepiece respirator, we measured about 11.1 kilovolts at between 50 to 100 nanometer distance from the sensor. SM is for a surgical mask, the standard surgical mask that you would find in a store. This one is also made from non-woven polymer fabrics, but they're not so electrocharged. They have very weak electrocharge characteristics. The isotactic polypropylene that I manufactured with the cotton candy machine, without the isothermal charging, gave me a potential of 5.3 kilovolts. But after this isothermal charging with the system, it jumped up to 7.4. The mixture of polypropylene, polystyrene was higher, but after isothermal charging, it went up to 10 kilovolts. That was the closest I could get to the electrocharging, the static charge capacity of the N95 filtration layers. So you can see the last few slides have been more of tinkering and engineering than science. Once we had the fabric, the question was, okay, how do we translate this into a mask design? Unfortunately, I don't have a sewing machine, nor do I know how to stitch things. So what we did was we took this standard surgical mask that you see in the video, and we took this layer. We just put it like this on the inside, and people could wear it. That was one simple design of for common people. But there was also a shortage of N95 quality facepiece respirators in hospitals. So the second design was actually inspired by an open source 3D printing design called Montana Mask that I found online. You can find the STL files, as they call them, from this link here. And here you see basically the layout for these masks on mask holders, as I call them, on a 3D printer. And this is the front and this is the back side. So I have, if you look at my video screen, you can see one 3D printed mask holder that I'm holding. So basically, this is how it looks. And you see these hook-like holders here. You can have your elastic band over there. And you can take this electrocharged layer and put it against this frame and just push it back. Yeah. So I just hold it like this, and so for the purpose of showing to you, I just did a quick hack thing. But what we were doing was basically we were cutting up this fabric into four, and we used into 4 parts like this, and 5 centimeters by 5 centimeters square patches, and then putting it. So, and these worked much better. I'll show you the results in the next slide or the one after. So these were the 2 designs that I played with. So I have gone from being able to manufacture, fabricate this electrocharged layer and induce charges in them and then translate into some mask design. Now is the characterization. So as I mentioned, I skipped ahead a little bit. So here are the results. So I was trying to study the structure of these electrocharged filter polymer fabrics. I'm showing you the scanning electron micrographs for these. The one on the leftmost top left corner is from a commercial N95 electrocharged fabric. It was a 3M mask, sorry, N95 respirator from 3M. The one in the middle is from isotactic polypropylene, and one on the right is from the polypropylene polystyrene mix. The one thing you notice is that the isotactic polypropylene seems to give me more straight nanofibers compared to the N95 layer, which seems to be more tortuous. But what I found was, if I played with the percentage of polypropylene to polystyrene, 80% polypropylene and 20% polystyrene gave me this kind of tortuosity, which sort of comes close to what we observe for the N95. So trying to understand what was the difference between the polypropylene and polystyrene, I looked at the structure for the low crystalline polypropylene and pure polystyrene. And you notice that pure polypropylene gives me very straight fibers, whereas polystyrene gives me very convoluted fibers. So I figured that by mixing 20% of polystyrene with 80% of this was giving me something close to what we observed in the N95 layer. So my guess is that the N95 electrocharged layers are using a combination, a mix of some mixture of polymers that is their proprietary mix that they will not disclose to any of us. But I was by trial and error, I was reverse engineering, trying to get as close to it as possible. I think the difference in the tortuosity of these fibers would impact the porosity, but we will see if how that affects. But to give you an idea, since there was a question about the fiber radii, for the commercial N95 layer, I got about 4.1 microns mean radius for the fibers. For the isotactic polypropylene, it was 4.54, and you can see I don't come as low as the N95 mean radius, but it's close enough. So by trial and error, we were able to figure out how to get close to the N95 quality material. So now that I have done the structure, we did the filtration tests, and I'm showing you a snapshot of an early design that sort of did not work. We scratched our heads. And for this, I got a lot of help from actually Shankar Ghosh. So here you see that initially for the particle counter, I was using what is used for counting particles in clean rooms. And after chatting with Shankar Ghosh, I realized this was a mistake because they can only count particles of diameter 5 microns and above. Whereas for the N95, you have to go up to 0.3 nanometers. So the final design was, as in the schematic shown here, I was generating aerosol particles in water with salt, sodium chloride. There was an air intake, so the mist is generated here. So this is the video that I took of one of my early tests. It was a $10 ceramic piezo thing that you just put it in water and it atomizes the water and gives you this mist. It's that simple. So there's an air intake and there's a valve so that I can control the amount of aerosol particles going into a confining box. There is a second air intake so that I can mix the aerosol particles with just pure ambient air. And then I got hold of a mannequin head from a storefront. You know, these retail stores, clothes stores have these mannequins. I just took the head. I drilled a hole in the back of this mannequin head right up to the mouth. And that was connected to a box with a PM2.5 monitor. There was another PM2.5 monitor in this confining box. So what is the PM2.5 monitor? So this was the monitor we were using. The PM2.5 monitors, basically these monitors are used to measure the air quality in homes and offices. And they use the same laser sensors used as used in very fancy commercial testing machines for N95 masks. except the difference is this monitor, if you look at my video here, it's telling me that there are about 33 or 34 micrograms per meter cube concentration of particles of 0.3 microns or sorry, 2.5 microns or greater. But this sensor since the laser sensor is the same that is used for N95 mass testing, we know that these sensors actually can measure, detect particles down to 0.3 microns or 300 nanometers. So this was an idea, again, I got from Shankar Ghosh. So the basic idea was, if I measure the concentration of particles using this monitor A, and that before they enter the mask, and if I measure the concentration of particles in this monitor B after they have gone through the mask and exited through the mannequin head, and I'm applying a vacuum to basically suck, since I cannot simulate the natural respiration, the inhalation and exhalation, we basically used a vacuum pump and sucked the air through the mask. So let me first show you the calibration tests, because this is not the industry standard testing device that is used by certification agencies, for example. This was homemade, but the filtration efficiency is usually defined as the penetration, which is the percentage of particles that have penetrated through the filter layer, and it is usually quoted versus the particle diameter. But since this PM 2.5 monitor only tells you how many particles per micrograms per meter cubed of particles are going through, it does not tell you what diameter of particles that you are detecting. So instead, what we did was we took a time series of the concentration in concentration for monitor B divided by concentration for monitor A times 100%. So that gives me the penetration, and we did it at 15-minute intervals over 12 hours. So here I'm showing you the data. This top plot is showing you penetration as a function of time over 12 hours at 15-minute intervals. This is for the N95, commercial N95 facepiece respirator. What we did was we used both charged as well as neutral aerosol particles. So when I use charged particles versus neutral aerosol particles, there is a difference in the measurement, the percentage of particles that are penetrating across. Also, typically the measurements are made at either 30 liters per minute, which is normal respiration, or 85 liters per minute, which is very high respiration. This is the specification given by the certification agency. So you notice that so when we say N95 mask, it says that 95% of particles of 0.3 microns or larger are basically filtered out. So the reciprocal of that is the penetration, which means if it is less than 5% penetration, then it is conforming to the N95 standard. And you notice that the neutral particles at for both flow rates gives me about little about 3% penetration. Charged particles do much better. It was coming out to around 1.5%. Now I repeated the same measurement, not with an N95, but with a surgical mask, this type of mask. So here's the thing that is often emphasized by all health agencies, and you can find it on this N95 Decon website also, which is the tight facial fit. This 3D printed mask can give me a tight facial fit close to what the N95 achieves, but these surgical masks don't give me as tight a facial fit. There is basically these interstitial gaps through which the air can go. And naturally, likewise, you can see that I was seeing close to 50% of particles passing through, 50% of the particles at 85 liters per minute without, so there were two types of tests. One was just normal surgical mask as it is. The second was I taped it to basically reduce the amount of interstitial gaps. So when I reduced the interstitial gaps, the penetration fell to about 12% or so. So that was very encouraging, but it was nowhere below 5% as one would want. So these are never going to be close to the N95 quality. Now, let me show you the results from the two designs that I mentioned earlier. So this, the middle plots, the two middle plots are for polypropylene material. The right side plot in red is for polypropylene polystyrene mix. The top one in the middle is for the 3D printed, is for the surgical mask with, so basically I removed the electrocharge on one of these layers using a static eliminator and made the measurement with it. So you see non-electrocharged layer measurements at 30 and 85 liters. They give me a measurement of about 12%. So for these tests with the surgical mask, everything was done by taping it so that I don't get any interstitial gap. That's why I'm seeing 12% penetration. When I use the electrocharged layer, so without the electrocharged layer, I'm getting about 12% penetration. With the electrocharged layer, I get about close to 7% or 8% of penetration. So the electrocharged layer definitely makes a difference. But it is still nowhere near, it is still higher than the N95 quality. The plot below where my spotlight is hovering right now is for the 3D printed mask with the electrocharged layer using charged and neutral aerosol particles. And you can see that almost all of them, except for the neutral particles at 85 liters per minute, they crossed the 5% mark, but the other three were below the 5% mark. That is for polypropylene. For polypropylene polystyrene mix, I get more or less the same results as I get for polypropylene with surgical mask. But when I look at the 3D printed mask results, the extra charge retention of polypropylene polystyrene actually takes it below the 5%. So this is 5% line. And for all 4 tests, I got below 5%. So this material did better than this to get me below the within the N95 mask requirement. So this is the main results from the characterization, which helped us decide whether one could achieve N95 quality and how important is this electrocharged fabric at all in getting there. One test I haven't shown here, and I'm in the process of doing it, which is to repeat the filtration test for the N95 mask, but by bleeding out the electrostatic charge on this, because then that will tell me how this will perform. It should go above the 5% mark. So I hope to add that in the next few days. So finally, the question was raised about the COVID-19 virus has dimensions of about tens of nanometers. So in the literature, it says that it could be between 50 to 200 nanometers. So the question is then, can a N95 mask or our 3D mask design filter out particles of that size? The fact is that the SARS-CoV-2 virion gets denatured under dry conditions. So it is only working against us when it is carried as hydrated aerosol droplets. So actually, we need not worry about the fact that it goes down to this level. But there were 2 papers which I forgot to cite here. I apologize. There were 2 papers which did test with another virus, which was 27 nanometers, and the N95 masks were able to filter them out. What I did was a proxy test. I used colloidal particles of 50 nanometer fluorescent polystyrene particles. This is a dragon green is the fluorescent dye. And I took a confocal image. So instead of the aerosol mist particles, I sent this dust of nanoparticles, colloidal nanoparticles in my filtration test. Then I removed the mask, the filtration layer, and I put this electrocharged layer under a confocal microscope and looked at it at a depth of 500 nanometers. And you can see there are lots of particles stuck along the fibers. So these are basically the fluorescent signal is showing me where the particles are stuck. So I think I'm almost out of time. So to summarize, I've tried to share a fabrication method for electrocharge filtration using common parts and easy methods. And the basic idea comes from a cotton candy machine. And we tried two types of materials with polypropylene or polypropylene polystyrene mix and two types of mask designs. And found that the 3D printed mask holder with polypropylene polystyrene could achieve the kind of filtration efficiency we expect for an N95 facepiece respirator. Ongoing work is a method to simultaneously decontaminate and electrocharge face masks made of any fabric, in particular homemade cloth masks. And I'm also working on what I mentioned earlier, which is try to get to the bottom of the physical mechanisms that underlie the filtration. Basically, what is really happening in these three physical mechanisms: inertial, impaction, diffusion, and electrocharge mechanisms, because I couldn't find any literature that really delves into the fundamentals of it. To acknowledge, as I mentioned, I got the idea in passing remarks from Maha in 2010 about the cotton candy machine. I got a lot of inputs from Shankar at Kolaba on filtration test. Noriko Ishizu and Kiran DC are the OIST engineering section, and they helped me with scanning electron microscopy and 3D printing. And the OIST imaging section helped me with confocal imaging. Sachin Velankar at University of Pittsburgh had lots of suggestions for me on the polymer materials. I'm not a polymer expert. I have never worked with that material, with these materials before. So this was totally new to me. So he helped me a lot with critical suggestions and reading of the manuscript. And I thank the OIST Graduate University for supporting the work. And I'm happy to share the preprint that is currently in review. If you send me an email at this email address, I'm happy to share it. But what I want to leave you with is that this is not rocket science. It's basically, it doesn't matter physics, and it's interfacial science, or shallow and superficial science. So with that, I'll stop and take questions. Sorry for I overran my time.
So, Shubhro, I cannot see the raise hand thing, so maybe you can handle the questions.
I'll do that. So, Vishal?
Yeah, hi, Mahesh. Very nice talk.
Thank you.
So I had a question regarding your experiment. And it comes from the fact that, masks are used both to protect ourselves, but also to protect others. So have you done the experiment in reverse, where instead of a pump, you have a blower, and you're looking at particles being ejected from the individual, and do surgical masks perform better in terms of efficiency then?
I'm afraid I haven't done that, but it's a beautiful idea. I should do it and invite you as a co-author, because the idea is yours. Absolutely.
Okay. All right. Thanks.
Yeah. Abhijit?
Hello. I have one question. So we see that, okay, so one, like as I understand, one problem with this N95 masks are they are meant to be disposable, right? So
yes.
It's a big challenge to decontaminate and reuse those. So question is so the material you are using for that charge layer. So like how good is it to hold the charge? Like if you use it for let's say 1 week, let's say normal use, let's say you go to shop or something, you sneeze, you touch it all the time. Then after that, how many days it can hold the charge?
So we started, that's one test I've been doing, and it is still ongoing. The first layers we made was around April 7th, and I've been testing the layers every day for the charge. So I showed you in this slide, in this slide, I showed you that there is the real charge electret and the oriented dipole electret, right? So the materials I used fall under the real charge. That means they have embedded charges in them. That does not die out. So you can leave it for months and it won't die out. But the charge that was induced through isothermal charging using this this isothermal charging method. That was decaying within about a week, and I realized that was due to humidity. And I have not done systematic tests yet by controlling the humidity, but what I could measure with the potentiometer was that the charge that we induced through these air purifiers was dying out. So that means that, for example, if my polypropylene layer gave me about 5.3 kilovolts, that remained throughout these 2 or 3 months. But if I induced this charge isothermally and took it up to 7.4, within about a week to 9 days, it would come back to roughly 5.3 kilovolts. So that much is being decayed.
I see. So I see. So, but so we know, like it is easier to charge metal than insulators, right?
Yes.
So if you, let's say, like small things, like if you pick up some small metallic object, let's say like a small coin or something, and if you charge it, and if you use like normal mask, like double layer mask, and you put a coin between those layers of like clothes, normal clothes, because you know,
Yes.
at least in India, most people use like absolute like handkerchief kind of a thing. So if you put a small coin, charged coin in 2 layers, how good it be?
I don't know how good it will be. I have not tried it myself, but this is one design. There are several ways to get there. I'm aware of one design by Professor Kulkarni in Bangalore, who used nylon. Nylon is also an electric fabric, but it's not coming from. It's woven. It's not non-woven fabric of this sort. But they were using triboelectric charging to induce charges. That also works. So there are many ways to put charges. And even here, when I said that the charge was the induced charge from isothermal charging would decay within 9 days, if I put it in front of this negative ion purifier for 10 minutes again the charge would go up. So what we were doing while giving away was we were just before giving it to somebody, we would charge it and give it to them and tell them that you should use it within a week. So there are many ways to do this. I just followed one way.
Okay, yeah. So I mean, it might be better if you teach someone that how to charge it easily. If you can use some object which can be charged easily, then it will be more efficient, no?
Oh, is it? Let's.
But this also takes on.
Later.
But even this material takes only 10 minutes to charge it. So it's not that it is difficult to charge it.
Yeah, let's
Thank you.
move on,
Thank
and
you.
we can ask later. Ranjini?
Hi Mahesh, very cool. I'm glad I got to find out about your mask at last. So my question was more of, about the fiber scale structure of the mask. So you showed us that the original N95, it has these tortuous fibers, right?
Yes.
So I mean that tortuousness is probably good for a smaller penetration. Is that correct? So then why not just use only polystyrene? Why use a mixture with polypropylene? Because polystyrene is giving you a more tortuous fiber, right?
Yes, but I could not get down to smaller diameters. You notice the scale bar. For all these images,
Yes.
it is 200 microns, but for this, it is 500 microns. These diameters are much higher. So I was getting 18.5 micron fiber radius, not diameter, radius.
Okay.
So
Okay.
I couldn't figure out a way to go down. That is the reason I realized in the last 2 days is because polypropylene is quite agnostic to changes in viscosity, surface tension, etc. above its melting temperature.
Okay.
Because it is a crystalline material, whereas polystyrene is a glass, and
Right.
once you go past its glass transition temperature, its viscosity is very sensitive to temperature. So I'm sure that if we tweak this, if I play with the polystyrene material, I can get fibers of much smaller radii with the same tortuosity and it has much higher electrocharging charge retention characteristics. So you're absolutely right. I think the way to go would be polystyrene, but if I can figure out the right temperature. There is another material there's a professor of electrical engineering at Johns Hopkins by the name of James West, who was playing decades ago with Mylar. And Mylar has extremely high charge retention characteristics. So I haven't played with that. I just found out about it by chance 2 days ago because he was using Mylar to make microphones. And if Mylar is also a type of polymer, so if I can play with that, that should also work. And I think that I suspect that it will do much better than polystyrene also. I had one of my goals in doing this was common materials and easy methods. So I stuck to materials that people can find around easily. So I did not go to fancy materials for that reason. But there are materials that with much better charge characteristics.
Thank you.
HRK?
I forgot to unmute my mic. Yeah, Mahesh, very nice talk. So enjoyed it. So the question is, how cheap is your fabric? Because this 3D printed design seemed like a nice idea because you can just, because this N95 mask, after you use it for a while, you have to throw the whole thing. Whereas the thing you had, you could just replace just that cloth, and that seemed very nice. But how cheap is the cloth?
The fabric is actually quite cheap. As I said, I was using polypropylene from these bottle caps. The ones we sourced commercially from Sigma Aldrich was of the order of $50 for 5 kilograms, and this one is about 12 grams. So you can make lots of fabrics with 1 kilogram, which would be about $10. So it's very cheap that way.
I see. Very nice.
The most expensive part is actually this, but you can reuse it. So what we were doing was we were giving away this to people who had cloth masks or surgical masks, but we were 3D printing these on campus for hospital staff, healthcare workers. And you would say just replace the filtration layer every day and keep going with it. So that worked better.
Okay, thank you.
There was also one French group that took these layers and they used, what do they call, snorkeling masks, and they cut holes in them and they basically fixed these and they used those.
Abhishek?
Yeah, so Mahesh, I had two kind of related questions. So basically, when we cough or sneeze, what is the typical size of droplets that's generated? And the other related question was, how effective are commonly available masks, which just is like few layers of clothes? Are they at all useful in at least stopping some of I guess it stops some of these droplets, but then the question is, what is the distribution of the size of the droplets?
So I don't have the data with me, but that has been published actually. There are 2 papers which did this with not with homemade cloth masks, but with the surgical masks, and the distribution ranged from about 30 to 50 nanometers up to a micron or so. And these masks were not doing so well. Basically, the filtration got worse as the particle size fell, and it was of the order of 40 to 50%. So it's not very different. It's not far off from the result I got for this plot over here. So let me just so you see the bottom left plot. This was for a surgical mask, and if I just wear the surgical mask on the put the mask on the mannequin head without taping it, I'm basically roughly 50% of the particles are able to pass through. So they don't do so well. And this study was showing that cloth masks were also behaving similarly. The take-home point is that it has nothing to do with the quality of the mask, but the gaps in between. Because you don't have a tight facial fit, the penetration increases.
Okay.
Okay, I have one more written question from Siddharth. I'll read out the question for you. And so the question is how to remove the particles that have been collected. For example, can you wash it? And a follow-up to that is how to ensure that the particles do not break and enter the respiratory tract. Any precaution done on this regard, since it was also distributed to colleagues?
So these are not washable. I did try washing them, and it's not that it comes apart, but I tried washing the commercial surgical mask, and this holds pretty well. But the ones I made with the cotton candy machine would degrade more easily, and I suspect that is because there is some bonding that is going on in these kinds of materials that I don't have access to. About particles passing through, I don't have any good ideas. What we were saying was basically from the penetration tests, they were looking good for about 12 hours. If you look at this plot, what I haven't seen is at some point it should start decaying. That means, or rather the penetration should start rising because there is no more filtration efficacy left. And we were advising healthcare workers especially to not use it for more than 8 hours. We were asking them to replace it after every 8 hours. So we did not go into, you will notice that I did not put my name, but all this was one-man army effort. I was doing everything by myself for the most part. But I did get a lot of help with the characterization study for the scanning electron microscopy and for the confocal. So I'm rate limited because I have only 24 hours and two hands. So I did not get into many details that I would have otherwise liked to get into.
Sorry, Mahesh, if I understand the question correctly, I may be wrong. The question is, what about the fiber splitting off from this and going into the...
I see. I see. I'm sorry, I misunderstood. We did not see any fiber splitting off from this and going in because we did basically what I don't have any strong proof, to be honest. But did I see? Let me think. That's a very good question. No, I don't have any proof at all. So that, yeah, that possibility exists, I'm afraid. You're right. And the fact that I don't have any bonding material like that is used in these surgical masks, I'm not using any bonding material, so the risk is certainly there. So that is something I definitely need to look into.
Okay. Abhishek, you have one more question?
No, sorry, I forgot to lower my hand.
Okay. So any more questions from anyone else? Okay. If not, let's thank Mahesh once more for this nice talk. And thank you, Mahesh.
Thank you very much.